Okay, if our flow data leads us to a curve that looks like this, it's clearly not a power function. It's going to be very clearly not be exponential. It's not going to have any of the characteristics that we want. But we know, among other things, that a power function has zero slope at the origin. So if there's a place on this curve where we reach zero slope, of which there will be, because at some point the curve will, or the flow will stop and the depth will stop changing, which means that the depth is going to remain constant from then on. If this is the first place at which the slope is zero, so I could say this is the first zero slope that we encounter on the graph, the point at which we are pretty sure the slope has reached zero. And we can actually determine that by looking at the slope graph. And the slope graph will be zero at this value of t. This would be a graph of depth versus t, not x. Although we could say that x represents time. It's just better for our attention if we call it t. Anyhow, it's no big deal. We get this graph, and this is just like the graph that you made for your own data. Now, if we take this graph, we can transform it. We can move it without changing its shape. What we want to do is move it without changing its shape so that this point of zero slope goes to the origin, and the graph, instead of being in the negative direction, is in the positive direction, like the graph of a power function with a zero slope at this point. So we're going to do that. So I gave you the instruction now in order to understand how to move the graph. I'd take 4 points on the graph and I'd say we want to do the following, and I number the steps 1, 2, 3. I started by reflecting each point through the y-axis, but then I decided that wasn't necessarily the best idea. I want to start by shifting each point. So what I want to do is take each of these points on the graph, each of the points represented in purple, and I want to shift each point by this arrow. Now, what's this arrow? This arrow is the same as this arrow. It's the same color. It represents the same arrow. It has about the same length, as best I could estimate it. Now, this arrow is equal and opposite to this arrow. But in any case, this arrow represents how far you have to move this zero slope point in order to get it over to the y-axis. Now, we're wanting to move this point to the origin, so moving it left over to the y-axis is a really good start. So we move this point over to the y-axis, and we move every other point in the same way. So each of these points, well, here's your green arrow, goes from here to here. So each of these points here translates, well, I don't have green arrows now, but each of these points translates according to the green arrow. So we take this point, apply the green arrow, that moves it to the y-axis. We take this point, apply the green arrow, that moves it, well, obviously to the left of the y-axis, since this point is to the left of this one, and it moves these 2 points. So we have these 4 points right here, which kind of give us this curve. Okay, so we've got the same shape. Curve has the same shape if we draw it through the points in the same way we drew this one. Then what do? We shift each point by this downward vertical shift. Okay, so right here is the downward vertical shift, and this is the distance. This shift goes through a displacement that takes this point to the x-axis. Now, since we move this point over here, if we move it down that distance, it's still going down to the x-axis, and it's going vertically, which means since it's on the y-axis, if we move it vertically down to the x-axis, it's going to end up at the origin, isn't it? So this point here takes this vertical displacement downward. This one the same thing, this one the same thing, this one the same thing, and now our curve is this. Then what do? We reflect through the y-axis. So we take this point through the y-axis to an equal distance on the other side, moving always perpendicular to the y-axis. We do the same with this point, we do the same with this point, And I think I have 1, 2, 3. Okay, well, and yeah, we got a fourth point, but that's the origin, and the origin's already on the y-axis, so when we reflect it, it doesn't have to go anywhere. So we got 1, 2, 3, 4 points in our graph. Now we draw the curve, and now we've got a curve that we can test to see if it's a power function. And if this is a power function, then we can use these shifts to construct, well, to get the algebraic expression for the function in a way we might not actually have time to get to in this course, but in a way you'll see in subsequent courses if you haven't already. So now we can test this thing to see if it's a power function. Take a couple of doubling x values, see what the ratio is. Double the x value again, see what the ratio is. Doesn't look like this one is a very good power function, just taking a look at it. But if you do this for the actual flow data, you will get a very good power function. So the flow data will give you an excellent power function if you've got good flow data.